This is the first of a series of lectures in which we will present a certain number of ways of visualizing functions. The sections will be numbered 0.2 and then a letter indicating the order on which this lecture should be followed. We will using 3D animation in order to show better the visualizations. The first lecture is an introduction of the possible ways of visualizing a function. So there are several ways to visualize a function f from x to y in order to highlight its action on elements of the domain. Remember that the function is defined by its action on the elements of the domain. So assigning a function means letting the other person know the images of each element of the domain X. So the most common techniques for representing visually a function are the following. One is drawing the domain, drawing the codomain, and then some arrows from the domain to the codomain, representing the images of few selected elements in the domain. This representation has lots of drawbacks. Among them, we can name the fact that we just highlight the action of the function on a finite number of elements in the domain, all those that we can actually choose and pick. Therefore, we certainly are not able to have a global understanding of the action of the function. The second most common way of representing a function is just drawing the image of the function. So I recall that the image is defined as the set in the codomain. You see are the elements b in y. Y is the codomain of f. So are the elements of y, for which there exists an element a in the domain, for which f of a equals to b. The third way of representing a function is drawing the graph of the function. So remember, we have seen the previous lecture that the graph is a subset of the cross product, the Cartesian product of the domain and the codomain. And indeed, it will contain all the informations of the function f. There is no information carried by the function f which is not highlighted in the graph. In fact, the graph is the mathematical definition of function. As we have seen in the previous lecture, we have a, let's say, hand-waving representation of f, a hand-waving definition of f, which involves the use of terms like a law or a correspondence between elements of the domain and elements of the codomain. And this hands-waving definition is equivalent to the mathematical definition of a function, which is what we called the graph of the function. So the graph is actually a subset of a Cartesian product of the domain times the codomain. Therefore, in most of the cases can be drawn, since it is a subset. In the coming lectures, we will analyze the representations of the function 1, 2, and 3 for the following test functions. So in order to highlight the properties of these representations, we choose the following functions. So the first one we call f, and it is a function from the real numbers r to the real numbers r. So the domain is r and the codomain is r also. And it is defined commonly as f of x equals to x squared, meaning that for every number x in the domain, f associates its square in the codomain. The second function is going to be named g, and it will go from a subset of r squared. More precisely, it will go from the non-negative part of r times the real numbers r. So it will be a half plane comprising all the points x, y, where x is non-negative. And it will associate to any pair of numbers in that set, it will associate a real number. Its definition is the following: g of xy is equal to the cosine of x plus y plus the sine of x times y minus 0.1 that multiplies the square root of x minus y. Now it is quite involved definition, but this is just to give a particularly nice looking shape to its graph. The third function is r, and it will go from the real numbers to the plane r squared, and it is defined as r of x equal the pair of numbers cosine of x comma 2 times sine of x. So notice that since the domain are the real numbers, I choose 1x in the real number, so a generic number, and I have to associate to it an element of r squared. So it is a pair of real numbers, and this pair is precisely cosine of x comma 2 sine of x. The last function is h, has as the domain r squared, and codomain again r squared. Therefore, to a pair of elements, pair of numbers x, y, I will be associating another pair of numbers defined as 1/2 times x minus square root of 3 divided by 2 times y, comma, square root of 3 divided by 2 times x plus 1/2 times y. Before beginning analyzing each of these functions, I want to mention about the relations between a domain, codomain, and the graph of a function, since all of them will be involved in the visualization of the function itself. So let f from a to b be a function between sets. Then there is the following commutative diagram. So the diagram involves the objects, sets in this case, a, b, and graph of f. On the top we have our function that goes from a to b, and it is the following arrow, and we call it f. On the bottom we have graph of f, and we have two maps going one from a to graph of x, which we will call I, and another map going from graph of f to b, which we call q. Saying that this diagram is commutative, it means that anytime I go from one object to another, taking two different routes, I will be getting exactly the same map. So in this case, the only way I can go from one object to another taking two different routes is going from A to B, and one route involves taking just the map F, and the other route involves taking first the map I and then the map Q. So saying that is commutative simply means that if I take any element in A and apply F, I end up in B. That element that will be the image of this element in A is exactly the same element I will be getting if I first take I of this element in the graph of F, and then I apply to this element Q. This means commutative. Let's try to understand how the maps I and Q are defined. We fix an element x in A. The map I associate to x the element on the graph given by x, comma, f of x. So remember, graph of f is a subset of the Cartesian product A times B. Therefore, all the elements of graph of x will be pairs, where the first element is an element of A and the second element is an element of B. So certainly x, comma, f of x is an element in the Cartesian product A times B, and by definition of graph of x is also an element of graph of x. Remember that all the elements of graph of x are of the form an element of the domain, comma, the image of that element in the codomain. Okay, so x comma f of x is precisely an element of graph of f. Now, how do we define q? Well, we pick any random element in graph of f, which will be of the form a comma f of a for some element a in the domain of f, and we just project it to the second element f of a, so we associate f of a. It is immediate to see that if we apply first I, so to x we go to x f of x, and then we apply q, that means associating to x comma f of x the image f of x. It is exactly the same as taking an element, the element x, and applying f to it. Why is this diagram important? This diagram is important because highlights how we can recover all the information of f, knowing what its graph looks like. Any element of graph of x will be of the form a comma f of a. Therefore, knowing one element of graph of f means knowing one element of a and its image in the codomain b. This knowledge is related to a and b through these maps that I've just defined, I and q. Each animation in the following lectures will cover the following steps. The first one is drawing the domain and the codomain of the function. Notice the colors that I'm using here will be the same as the one appearing in the animations. Domain will be denoted in green, codomain as a whole will be denoted in red, and everything concerning the function itself or the graph of the function will be denoted in blue. So after drawing the domain and the codomain as sets, we will exhibit a few points in the domain and their images in the codomain. Notice the images will be purple because they are different from the codomain. Now this corresponds to the visualization technique that we described before, and we numbered with the 1. So it was the first visualization that we listed before. Then we proceed by drawing the set image of f as a whole, not just a few elements of the image, but the whole set of the image, and we will deduce it from the few points of which we displayed their images before. And displaying the image of the function f is the visualization of the kind number 2 that we described before. Second step is going towards the representation of the graph of f, and in order to do that we have first to create the set in which the graph will live, namely the Cartesian product of the domain times the codomain. Therefore we'll be moving them around in order to create and to display this Cartesian product. Finally, the last step is drawing the graph of f, and it will be blue just like the function before, by further exhibiting some of its points, and these will correspond to visualization number 3. So graph of f will contain infinitely number of points typically, and we try to understand the shape of it by drawing certain number of points. Then after we have understood the shape of the graph, we can describe explicitly the action of the maps I and q, which factorize the function f, as we have seen just a few minutes ago, and we will show their actions on points of the relevant domains by means of arrow drawing. Therefore, this is a kind of visualization number 1 that we said before, so we'll have few points and then arrows showing where these points are going to in the codomain.